is on another way of solving constraint satisfaction problems. This is called variable elimination. The reading for this was optional, and what I'm going to show you today is a variation on the algorithm that's actually given. It corresponds pretty closely, and we'll talk about the mapping, but I think this is an easier way to think about the variable elimination algorithm. So this is a constraint satisfaction problem, and this is just an expression of what the search space looks like if we were to simply use a search algorithm from chapter 3. This is a case where we have 3 variables. The domains of each are 1, 2, 3, 4. And we've got 2 constraints, that A is less than B and B is less than C. And there are 4 solutions in this case. A is 1, B is 2, C is 3. A is 1, B is 2, C is 4. A is 1, B is 3, C is 4. A is 2, B is 3, C is 4. So those are the only 4 solutions to this problem. And we could solve it by uninformed or informed search. And we talked about the GAC algorithm as another possibility. Went into some depth there. And so you can solve it using the generalized R consistency problem, but R consistency algorithm. But another way of doing it is known as variable elimination. In this case, here's the constraint network, and what we're going to do in this constraint network is we've got 3 variables, A, B, and C, and we're going to eliminate a variable one at a time until we get down to a single variable. And each time we eliminate a variable, we're going to incorporate the constraints that it has with other variables into those other variables, if you will. So let's say that we have this constraint network, and this is an example from the book, and we want to eliminate variable B in this constraint network. We collect together all the constraints that involve B, the variable that we've chosen to eliminate. And in this case, there are 2 constraints. A is less than B, B is less than C. Each of these variables has an initial domain, but some of these are not going to be achievable. So this row from involving A and B, this doesn't satisfy the A is less than B. This doesn't satisfy A is less than B. Some of these are eliminated right away. And what we do with the reduced sets is this represents the relation of A less than B. This represents the relation B less than C. We're going to do what's called in database a join of these 2 relations. And this is the join operator in relational database theory. A join in this case is going to look at a row in one of these relations or tables, and it's going to compare that row with all the rows in the other relation. And it's going to join based on all the shared variables. So the only shared variables between these 2 tables or relations is B. And so we're going to join this with any row in this table with a shared B value. So 1, 2 would join with 2, 3. And what we would get in the result is 1, we don't repeat B. B is the same value in each of these cases, and so it just appears once, 3. So joining 1, 2, 2, 3 would yield this in the result, 1, 2, 3. 1, 2, though, also joins with 2, 4. And so in the joined result, we get 1, 2, 4. In the joined result, we get 1, 3, 3, 4. And in the joined result, we get 2, 3, 3, 4. And those are the only 4 joins. So 1, 4, B has a value 4 here. There are no instances of B with a value 4 here. And so this row in A less than B relation does not join with any row in B less than C. And so it's omitted. It cannot be the case that B is equal to 4 and satisfies both constraints. And so what you have in relation R in this case is a set of values for A, B, and C which satisfy both of the constraints on which you joined. Now, what you do in this case is, since we want to eliminate B, is we're simply going to hide B. B is been taken care of in this. We have taken into account all the constraints involving B. And so we don't have to explicitly deal with B anymore. I say hide this because later we're going to reveal it, unmask it again, and because it's going to be part of the final solution that we want to return. In this particular case, the book doesn't do this part of the example, but just for completeness, I've decided to. What we want to do is we want to now eliminate another variable. We want to get to the point where we've taken into account all the constraints of all the variables except a very last variable. And when we get to the very last variable, we know we've taken care of all the constraints between it and other variables, and we can terminate the algorithm. So for completeness, we would eliminate either A or C. In this case, we might choose to eliminate variable A. This is really a trivial step because A and C share no constraints. There are no constraints explicitly between A and C other than what's already present in this relation. This relation itself represents a constraint between A and C, but it's really the only one. There are no additional ones. And so we can simply mask A, having taken into account all the constraints involving A and C, this one. We can mask A, we're left with one variable, we unmask all the masked variables, and we get a final solution. That's an example from the book of variable elimination. And this illustration, if you do go ahead and read that, that section, is going to vary a little bit with the algorithm that they present in the book. I present a recursive loop. I'm using a what amounts to an iterative loop. But this variable R roughly corresponds to what they mean by this variable or relation R in their algorithm. It is the result of joining tables representing other constraints. Let's look at an alternative ordering in eliminating variables, because you can eliminate the variables in any order that you want to, and you should get the same result. It may be more or less efficient to remove the variables in a different ordering, but again, the final outcome is going to be the same. So in this case, we might choose to eliminate variable A first. Variable A is involved in one constraint. It is A less than B. And when we look at that reduced set, this is the reduced set. This is the relation of the tables that represent the constraint A less than B. There's only one constraint to deal with. We've dealt with that. There's nothing other to join with. All right, there is no other table to join with, and so we're simply left with this table. And you'll see some examples in a moment on where we join with many tables based on many constraints. We hide A, and we're left with this relation. This is the result of eliminating A less than B. So here is that relation repeated. And if now we choose to eliminate B, there's one constraint involving B, it's this one. We would join this relation, which represents one constraint, and this relation, which represents another constraint, to get a joined result. Here I've simply flipped. I put R over here and B less than C over here, so the B rows are adjacent, and you can see a bit more the correspondence between these rows. But in this case, b equals 2 in this constraint table would join with b equals 2 in this row. And notice that there's only one shared variable between these two relations. It's b. So again, we're just joining on the value of b. Again, a is hidden, but I've sort of revealed it here with a transparent overlay. So what we get in the result is 1, 2. 1 is hidden, but it's still present. 2 for b, that's shared, and then 3 for c. This also joins with 2, 4, and so we get 1, 2, 4 in the result. This joins with 3, 4, and so we get 2, 3, 4 in the result. And this joins with, actually, that is that's a typo. I'll fix that. This also 1, 3 joins with 3, 4, and we get 1, 3, 4 in the result. So this should read 2, 3, 4 for this last row. That should read 2, 3, 4 for the last row. So just note that typo there. Once we do this, once we join it, this is the joined relation. We hide b because we've taken care of all its constraints, the one that was in R and the one that was in b less than c. We've got one variable left. We would unmask the ones that we've had, and we would get essentially the result that you see there, except this last row would be 2, 3, 4. Okay? So those are solutions to the same problem that give you the same result with perhaps a different number of steps. Let's go back and revisit the crossword problem. One of the problems was not just to solve this with the GAC algorithm, but also solve it with variable elimination. And just to remind ourselves about what this problem is, we've got some number of variables here. 1 across is a variable, 1 down is a variable, 2 down is a variable, 4 across, 5 down. These are all variables that I've represented here. For simplicity, the book has given us a limited set of words that we have to deal with. We would go ahead, if we wanted to, and make this domain consistent. And so the initial domain of 1A, when we start this algorithm, would be only 4-character words rather than 5-character words. So to make a domain consistent is to take into account the unary constraints. That the words match the length of the words and characters match the number of characters for the corresponding crossword path. Again, this is an image you've seen before. I crossed this out to make sure there's no confusion. We're not going to be talking about the GAC algorithm, but the slide was one I gave you for the GAC algorithm. But these are the set of constraints right here. And I could cross those out because those aren't really relevant to variable elimination. But these constraints are relevant to variable elimination. We're going to go through a couple of partial solutions to this crossword puzzle using variable elimination. So we're going to go back to the course schedule. But here's an exercise that perhaps you'll see for the assignment that's due on Saturday. Perhaps you'll have another assignment. But an exercise is to do variable elimination on this considerably more complicated network and find a solution for it. And hopefully you'll be better prepared to do that after we go through these other examples of variable elimination. Let's take a look at solution 1. Just written this out by hand, but again, we know what the variables are. And in this particular solution, I'm going to start by eliminating variable 1D. And the constraints involving 1D are these, that the first character of 1 down equals the first character of 1 across. The second character of 1 down equals the first character of 3 across. Third character of 1 down equals the second character of 4 across. And the fifth character of 1D equals the first character of 6A. And again, let's see, we can, that's tiny. So this just represents, you take a look at one of these constraints that the fifth character of 1 down, 1, 2, 3, 4, 5, equals the first character 6 across, okay? So I won't be referring back to that image very much. Here are the extensional representations of these constraints. And you'll notice that some things that were in the domain of 1 down initially cannot be in the relation that, that the first characters of 1D and 1A are equal. Because in the domain of 1A, there is no word that begins with U. And so this is a kind of arc consistency step that would happen in constructing this relation. There is no way of pairing usage in 1D with anything in 1A. There's no way of pairing usage in anything in 1A with first, or anything that begins with F for that matter. And so we would do this arc consistency step initially. The book talks very briefly about, or just mentions the fact that you can use them together, and that's an example of what we're doing here. Here is the relation that represents the fact that the second character of 1D equals the first character of 3A. This is the sense. The second character is E. There is nothing in the domain of 3A with a first character of E, and so we can eliminate that. So these are the relations, the four relations representing the four constraints after a simple arc consistency step between them. And what we want to do in this case is, again, these are extensional representations of each of the original, or each of these constraints involving 1D. And the idea is that once we've gone through this step, we have taken care of and taken into account all the constraints involving 1D. And so we don't have to explicitly worry about it again. And so I do the join across these four tables. And this requires 3 joins. Joining these two, take the result, join with this, and then take the result and join with that. So join is a binary operator, but presumably you can see how it works. Here, there is, if I look across these relations, there is one common variable in these four relations. And so that's going to be the basis of my join. So if I take a look at dance and desk, this is one row here, and I ask, can I join this with anything in this table based on 1D? And the answer is yes. This can be joined with this. And so this gives me a composite row. Dance in the 1D value for 1D, desk is the value for 1A, and add is the value for 3A. But notice that dance does not appear in this third relation. And so while this joins based on a shared value of 1D, dance does not exist. It's been pruned out. in that R consistency step does not appear in this table. And so this composite row cannot join with anything in this table, and so it simply falls out of the join. Dance will not appear in this bottom table because there is no, there are not common rows across all four tables with dance. The same with perhaps some of these others. Let's look at sense. Sense does not join with anything in this table, so sense will not appear in the final join. Haste will join with this row based on a 1D, same 1D value, but it does not appear here, so it will not appear in the final result. Sound will join with sound here based on a common 1D value. It will also join with this row based on a common 1D value, and it will also join with this row based on a common 1D value. So we have a composite row, sound soon, sound on, sound fuels, sound desk. And if I write that here and I don't repeat the 1D values, I get a composite row based on that join. Now you notice that there's something else in this table with a 1D value of sound, and so this composite triple will also join with this row in the final constraint. And so I have another row involving sound, except with a different 6A value. Dance will not join. I think we've gone through dance. It joins with this, but fails there. And think will join. Again, think this will join with think he, which will join with think first, which will join with think kind. That gives us one row. But notice that there's a second row here. So think this will join with think he, which will join with think given, which will join with think kind. And so that will appear here. And those are the only four rows that will appear in this composite join. And at this point, I have eliminated 1D. And so I've just put a box around it as just a way of indicating that I've hidden it. It's something that's been taken into account. And now I choose to look at 6A and eliminate that next. When I look at 6A, 6A is involved in one relation. It's the one I just formed through eliminating 1D. But this is a constraint, if you will, involving 6A. It's not a binary constraint, but it is a constraint. It's a relation that's been formed. And I'm just indicating that a relation like this, 6A, if you look at the separate table, does involve 1D. But because I've taken 1D, I've looked at 1D and taken into all its constraints, this constraint has already been taken into account in this table. And if indeed you look at location 1 equaling location 5 in D, D equals D, D equals D, K equals K, K equals K, that's already been taken care of. I don't have to do anything else with that. But there's another constraint that was not looked at when we took care of 1D, and that's 5D. So the third character of 6 across needs to equal the third character of 5D. Here's that constraint given here. And again, I would join, so I have two constraints, one that was constructed from an earlier step, one that is given separately. I would join these two tables based on shared 6A values. So desk will join with desk. And so I have, this is a composite row in the result table. This row will also join with this row. And so I've got a composite row representing that join as well. Dove will join with Dove here. And so I've got a composite row based on a shared value of 6A. Kind will join with kind here. And kind will also join with kind there. And so I've got two composite rows based on kind. But it's not just, I just don't join this row with this one and this one, but I join this row based on a shared kind value with this one and this one. So I've actually got four values of kind here. In general, joining can either grow the table, increase the size of the table, or reduce the size of the table, or leave it the same sometimes. At this point, I've taken into account all the constraints involving 6A. And now, let's say I want to eliminate 4A. This is the next variable I want to eliminate. I've got two variables that have already been taken into account. And there was an initial constraint involving 4A and 1D, but I'd already taken into account that constraint when in my first step, and so I don't really have to explicitly look at that. The other constraints are these two. The third character of 4A equals the third character of 2D. Here is that constraint after an arc consistency step. And this is the third constraint. The fourth character of 4A equals the first character of 5D after an arc consistency step. So I've got three relations representing three constraints on 4A. Two are binary constraints. The other is a n-ary constraint that I've created earlier. I am going to do the join, and now it becomes perhaps more explicit. I'm going to do what's called the natural join, which I've been doing all along. But in the natural join, we join based on shared values along all the variables that are common between the tables that I'm joining. So I would join this based on only 4A, because 4A is the only shared value between these two tables. And so fuels would join with this row in the join between these two, because there's a shared 4A value. And it would also join with each of these values as well, because of a shared 4A values. If I was just limiting myself to these two tables. When I consider joining either with this or with the composite rows created this through the join here, I'm going to be joining on both shared values, because you'll see that variable 5D is in this shared in this n-ary relation. And so I would do the join based on both shared 4A values and shared 5D values. So you'll notice that I can join this. I can join this row, fuels loses, with this, because there is a match on both 4A and 5D. And if you take a look at the result, because fuels also matches 4A, we should have sound soon on fuels, desk loses, and then a 1 there. This is the composite row that stems from joining this with that, okay? And that would be in the result. Notice that for 5D, there is nothing in 5D in this relation with haste. And so this row from this relation would not join with anything in this row or in this table. And so this would fall out for that reason. It does match 4A there, but it does not match both 4A and 5D there. And so all of these rows that are crossed out are either failing a test between a match here and a match there. In most cases, it's going to be a match there. Most of these are failing to match 5D when we join. But when we join based on all three of these tables, it doesn't matter the order in which you do the join, but join this with that, perhaps with that. These are the resulting rows that you would get. Just two rows. And so we're close to if there is only one solution to this problem, we're very close to getting that one solution. If this ever goes to the empty set, there is no solution. If this goes to a single row, there is a unique solution. If these two rows remain as candidates after you've eliminated all the variables, then there are two legitimate solutions to the problem. And if there are more than that after you've eliminated all the variables, there are that many solutions. In general, there could be a number of solutions, viable solutions to a constraint satisfaction problem. Again, I continue to eliminate, and when I was all done, I would just reveal these hidden variables, so to speak, and I would have my final solutions. I'm just going to point out that there is another solution here. In this case, the same problem, but just eliminating the variables in a different order. In this case, we're choosing to eliminate 2D first. These are the constraints involving 2D. And this is their extensional representation after a arc consistency check. And we can do the natural join across all three tables. We're just going to be joining, there's only one shared variable name across these. And so we would be joining based on a shared value there. So you'll see that help ETA would join with ETA at, which would join with ETA usage. And so we get one row there. This her joins with her he, which joins with her first. Soon one joins with one on, which joins with one fuels. And so in this case, there are no multiple rows that any of these could join with, and so we get a table which is the same size. We hide 2D, we've taken it into account. I'll just go through one more step here and have you finish it up, but we might eliminate 3A next. Now, we've got this one relation involving 3A. You don't have to choose variables that have been created in a prior pass. I might post an example of when you wouldn't do that, but see if you can, perhaps we could have chosen to, if this was a relation that we had, we could have chosen to next eliminate 5D, which may or may not have involved any of these. So we don't have to continually select things which have been created in a prior step. It will still work out just fine. But I'm doing that just to simplify it somewhat. Here we might eliminate 3A. Again, we've got one constraint, ternary constraint involving 3A. And we've got another constraint involving 3A. We join based on like 3A values because 3A is the only variables only variable that it shares. So this row would join with this row would join with this row would join with this row. So we're getting a lot more determinism in this example than we necessarily had in the last example. And we would get these three composite rows. And I eliminate 3A and then go on to eliminate 4A next, and you can complete the exercise. I would encourage you to complete it, and I would encourage you to go back and, even if I don't assign that earlier graph example as a problem for the assignment, go look at it and see if you can do at least variable elimination on a few of the first steps. Try and eliminate a couple of variables in that problem and convince yourself you could do it.